Hi, all right, we're talking about kinetics and collision theory, and we are looking at the different premises of collision theory. And the first one was that they must collide, the second with sufficient energy, and now the third is with molecules must collide with correct orientation. Okay, bonds have to be broken. That requires energy. Bonds have to be formed. That requires attraction. Remember, energy is required to break. Energy is released when they're formed. So to form requires an attraction. So these molecules have to hit in a favorable orientation or angle in order for that attraction to be maximized. And so what this picture shows is if they're hitting this way, A hits B, there's enough of a force of attraction there that A and B can then react. That'd be kind of like two diatomic molecules, maybe hydrogen gas and chlorine gas, and if they hit in the appropriate way, they can break these bonds, taking energy, and form those bonds, releasing energy. Now, if they hit the opposite direction, there just isn't the sufficient energy of attraction to overcome all of the other energy barriers. So it won't happen. So let's summarize those factors. First off, molecules must collide. Secondly, they have to collide with sufficient energy. We call the activation energy. And thirdly, they have to collide in the correct orientation. Now, we're not going to cover all of the mathematics involved in this. We'll save some of it for when you have that opportunity to take AP chemistry. But we're going to talk about a few of them as we go. Now, what the next segment then does is talk about some of the factors that affect the rate of a reaction and how those can be explained using collision theory. So what are some of the things we can do in the lab, in a production facility, in order to speed up the rate of a reaction? Now, the first one is the type of reaction, the nature of the reactants themselves. So some reactions are inherently fast. We've seen some, remember we've seen some of those precipitation reactions. A double replacement often involves precipitation or the release of a gas, and those happen, certainly with our ability to observe them, they happen instantaneously. Okay? There's no change in oxidation numbers. And for an ion, the oxidation number is the same as the charge. That's not true overall. Oxidation number is bigger than that, but for what we'll be looking at, we'll focus on things that are charged and ionic. All that happens is the reactants change partners to produce the products. So that's pretty quick. Now, most of the others, a synthesis, decomp, single replacement, almost always, not always, but almost always involve the exchange of electrons. They change oxidation number. And way back when we talked about this, we called them redox reactions. Okay? And these are usually much slower. Now, in the lab, we've done that before. I don't know if you remember, but we put some zinc into some copper solution, and it took quite a while before you saw that solid copper plating out on the surface of the zinc. And that's because they tend to be a little slower. And just as a brief reminder, remember, reduction is the gain of electrons. So the oxidation number becomes more negative because you are gaining electrons. So if you drew like a number line like this, since electrons are negative, when you become more, when a substance becomes more negative, you've got to give it those negatives. And if it becomes less negative, it's because it lost those negative electrons. So oxidation is the loss of electrons. The oxidation number becomes more positive. So back to our number line, this would represent, so if this is 0 and that's positive and negative, typical number line, right? This would be reduction and this would be oxidation. And I found a fun picture of an oil rig because in Texas we use that little mnemonic device. Oxidation is loss, reduction is gain, or oil rig for remembering that. So that's one of the factors that we have. And I'm going to go ahead and do two quick examples. We have the synthesis of iron 2 sulfide from pure iron and pure sulfur. And if we look at the iron went, remember pure elements all by themselves are 0. So the pure iron is 0, the pure sulfur is 0. We already saw from the name that iron's +2, sulfide is -2. So the iron became less negative, so it lost electrons. So we say that this species, the iron 0, you have to be very specific. Iron 0 or iron metal was oxidized. And the sulfur went from 0 to -2. It became more negative, so that was a gain of electrons. And that meant that the sulfur 0, the pure sulfur, was reduced. Now, when we take magnesium plus hydrochloric acid, now that's a single replacement. Magnesium 0, hydrogen's +1, chloride's -1. Well, magnesium wants to become positive. Magnesium likes to give up electrons, so it's going to steal the chloride, which leaves hydrogen all by itself. So magnesium becomes +2, chloride is still -1, and the hydrogen is 0. So magnesium became less negative, so it lost electrons, so that's oxidation. The hydrogen became positive to 0, that's more negative. That's a gain of those negative electrons, and that's reduction. Okay, quick review of types of reactions. It will help with some of the testing that we're ultimately preparing for. So we'll go into the next factor in our next video. So until then, this is signing off.